Hello everyone, I'm Yuxuan, an undergraduate of Nankai University. I'm going to give you a presentation. The topic is improving deep learning-based password guessing models using preprocessing. Passwords are common in our daily digital lives, and password-based authentication will remain the most widely used authentication method in the foreseeable future due to their simplicity to deploy and easiness to change. Therefore, it is of great importance to understand password security. Password guessing attack can be divided into two types based on the target of the attack. The first one, called targeted guessing attack, whose goal is to crack the password of a given user as quickly as possible and focus on each user. The second one, called trolling guessing attack, whose goal is to crack as many passwords as possible in a given dataset under the limited guess number and focus on the whole dataset. The attacking models can be used to protect password security, for example, evaluating the password strings, generating similar passwords to confuse attackers. Our work focuses on trolling guessing attack. There are two classical statistical-based cracking algorithms. The first one is the Markov-based model. It records the frequency of different characters after the password substring in the training phase, and then generates a guessing password character by character according to the statistical frequency distribution. The second one, named probabilistic context-free grammars, short for PCFG. It divides each password into several segments according to the character types, and generates the guessing passwords by filling in the segments with the recorded strings. These two statistical-based cracking algorithms are efficient enough compared to brute force, but they still have some problems. The main problem is that their results rely too much on the training datasets. The improvement of computing power, deep learning-based models with better results are emerging. Two kinds of neural networks are often used. The first one is based on recurrent neural networks. To avoid gradient vanishing problems, we use long short-term memory instead. This model is easy to train. Just construct the corresponding label Y for the input password X. We use a picture to demonstrate this process. In this picture, the input password is ABC. We add the starting character BOS at the beginning and the ending character EOS at the ending of the corresponding label. Each character in the input password actually corresponds to the next character in the original position. The second one is based on generative adversarial networks, short for PassGAN. PassGAN consists of a generator and a discriminator. The generator captures real data distribution by building a mapping function from noise distribution to real data space and generate fake samples. The discriminator learns to determine whether a sample comes from the fake samples or the real data. PassGAN are trained in this way until the discriminator cannot identify the source of the data, which means the generator can be used to generate guessing passwords. Since neural networks are generally used as black boxes for learning features, a realistic question is how to extract password features effectively. Data preprocessing is a feasible way to solve this problem. Models can be divided into two types based on the smallest unit it handles during training and generating. Now the key challenge becomes to choosing the appropriate preprocessing methods to the more effective features. In this paper, we focus on how to extract features effectively by preprocessing. We first explore character feature-based encoding method. Character-level models usually adopt the one-hot encoding method, which cannot fully utilize the character features. Therefore, we propose a new approach based on the type of characters and the corresponding keyboard positions. Next, we add additional recognition rules to basic PCFG. Existing PCFG divides passwords mainly into 4 segments: letters, digits, special characters, and keyboard patterns. We propose a refined PCFG-based preprocessing method, which adds the recognition rules of words, website names, and years to enable a more comprehensive password feature extraction. Last, we perform a series of experiments on 9 models to evaluate different preprocessing methods. Our experiment was built on 6 large real-world password datasets, a total of 57 million passwords, 3 from Chinese and 3 from English. They are different in terms of service size, user location, and language, which suggests that our models can be used to well characterize different user-chosen passwords. This table summarizes the datasets we used in this work. We name each dataset according to its website's domain name. Here are some statistics about user-chosen passwords. Table 1 shows that the length of most passwords is between 6 and 9. Table 2 shows that Chinese users love to use digits, while English users love to use letters. Table 3 shows that the proportion of top 10 passwords, indicating that Chinese passwords are more concentrated. Firstly, we focus on character-level models, and the character encoding method is a feasible way to improve. One-hot encoding method only classifies different characters, but cannot fully reflect other character features. Moreover, the matrices converted by the one-hot encoding method are sparse. The main challenge for character encoding is how to distinguish characters and reflect their features with as little space as possible. Therefore, we comprehensively consider different kinds of character features and then propose a new character encoding method that represents each character in 4 dimensions. The first dimension represents the type of characters, where we use 1, 2, 3, and 4 to represent digits, uppercase letters, lowercase letters, and special characters. The second dimension is the serial number of the characters in each tab. For example, A to Z can be represented by 1 to 26 according to the dictionary order, and the digits can be represented by themselves. The third dimension represents the keyboard row number, and the fourth dimension represents the keyboard column number. The row number of the keyboard increases from top to bottom, and the column number increases from left to right. For example, for the capital B, its first dimension is 3 because it is lowercase. Its second dimension is 2 according to the dictionary order. Its last 2 dimensions are just the keyboard locations. Next, for segment-level models, the basic PCFG only divides passwords into letters, digits, and special characters. For example, the password at the top right should be divided into 3 segments. We use L for letters, D for digits, and S for special characters. The subscript represents the length, but it has some shortcomings, such as destroying the integrity of some segments and ignoring users' habits of creating passwords. For example, the string 1Q2W3E should be considered as a complete segment due to the adjacent of characters on the keyboard, and some users tend to use the corresponding website domain name as part or full of their passwords. Therefore, we added the recognition rules of 4 important password features based on the analysis. The first rule is year recognition. Years have been found popular in passwords and are likely to mix with digit segments during extraction. We count the number of the years from 1900 to 2100 and record the proportion of top 10 most widely used years in the table. Results show that some years occupy a large proportion, which indicates that users may focus on some years. Therefore, we use a new symbol Y for the year segment and extract digit segments with a length of 4 and values between 1900 to 2100. It should also be noted to set year recognition before digit recognition. The second rule is website domain name recognition. We also record the proportion of top 10 most widely used website domain names in the table. Although the website domain names are less concentrated than the years, some website domain names still account for a large proportion. The passwords with website domain names may be considered as strong passwords in the basic PCFG. For instance, the password CSDN.net is converted to the segment-level password L sub 4, S sub 1, L sub 3, and may be assigned a low probability of being corrected by basic PCFG. However, it should be extracted as a complete segment. Here we use WEB for the website domain name segments. To address this problem, we add the recognition of website domain names. First, common suffixes such as .com, .net are used to construct a suffix list, and then the complete website segments are extracted from the passwords according to the suffix list. Since the keyboard pattern is also a popular way in password creation and also be ignored by basic PCFG, we add the corresponding recognition rule. Furthermore, keyboard pattern with only one character type can be extracted completely by basic PCFG. So our refined PCFG focuses on the keyboard patterns with multiple character types, and the length is limited. We use an example to explain the extraction process. First, extract all the keyboard patterns, and then combine keyboard patterns that are adjacent both in passwords and keyboard location. It is also noted to filter out the segments that do not meet the length requirements. Here we use symbol K to represent keyboard patterns. The keyboard pattern has inherent limitations, but may extract wrong segments. For instance, the segment PASSWORD should be regarded as a complete segment, but the string ASSW would be recognized as a keyboard pattern. Our solution is to use a dictionary that contains common words and extract segments that appear in the dictionary from the password before the keyboard pattern extraction. However, the effect of this method depends on the quality of the dictionary. Once the dictionary does not contain the corresponding word, keyboard pattern extraction will still cause errors. Therefore, we choose to construct the word dictionary through the training set. We first extract letter segments in each password, and then filter out segments with the unqualified length. The frequency of each segment is recorded, and the segments with the unqualified frequency would be filtered out. Some recognition rules may conflict with each other. For example, the string 989 in the string 1989 is recognized as a keyboard pattern, and the string CSDN in the string CSDN.net may be recognized as a word. Therefore, it is essential to set a reasonable extraction order and begin with the least conflict one. since the year recognition may conflict with the keyboard pattern recognition, and the website domain name recognition may conflict with the word recognition. Our final recognition order is the year recognition, the website domain name recognition, word recognition, the keyboard pattern recognition, and for the last, basic PCFG recognition. So for the who precise, we first construct a website name suffix list and also a word dictionary. Then we extract in order, just only for additional recognitions, and merge successive unhandled segments. At last, we use basic PCFG to extract unhandled segments. We also analyze the frequency distribution of the extracted segments with frequency greater than 5 and verify that the extracted segments meet zip distribution. The formula for PDF zip is as follows, where f sub s is the frequency of the password, r is the rank of the password. Both c and s are constants, depending on the data size. To verify that the data conforms to this distribution, we use the first equation to the next one by using log formula, where log f sub r and log r are linearly related. The extracted results are sorted in descending order of frequency on 6 datasets, and the fitting results are shown here. Moreover, all the coefficients of determination, which can measure the fitting degree of the regression line to the sample data, are also shown in the table. The closer the determination coefficient is to 1, the better the fitting result is. Although the deviation of some segments is relatively large, it still can meet the PDF zip model in general. PCFG-based preprocessing method can be integrated with neural networks. First, character-level passwords will be converted to segment level. Both model training and generated data are segment level. At last, fill in the segment level data with the extracted segments to generate final guessing passwords. Use chunk segmentation at CCS21. Use byte pair encoding method to divide passwords into chunks that consist of frequently occurring characters. For example, if there are 3 passwords in total and each character is considered as a chunk at first, each iteration, 2 adjacent chunks that occur most frequently would be merged as one chunk until average length of all chunks is greater than the threshold value. So for the first iteration, chunk A and B will be merged as one chunk. BPE algorithm can also be integrated with PCFG. For instance, passwords are divided into different chunks by BPE algorithm, and each chunk is converted to segment level by PCFG. It is also important to note that if there are multiple taps in a chunk, its final type needs to be converted to the number of segment taps plus the length subscript. The final result can also be used to train neural networks. Now we present our experiment results. To extensively evaluate the effect of 5 different preprocessing methods, 50 million guessing passwords are generated from each model. The experiment results on 6 datasets show that our new encoding method does not perform well, which can be attributed to 2 reasons. First, the sparsity problem caused by the one-hot encoding may not have serious side effects because passwords are generally short in length. Second, since our new encoding method is only used to represent each character, its advantage, which reflects multiple character features, has not been fully utilized. Using PCFG for preprocessing can improve the effect, and the LSTM-based model with our refined PCFG is even better than with the basic PCFG, which indicates that the fine-grained rules can extract more effective features. For our future work, firstly, new training methods to match up with our new encoding method can be a viable direction due to the underutilization of the character features. Secondly, we still think that encoding method would be a feasible way to improve the character level models. Third, the research on PCFG-based preprocessing method should be more fine-grained. One viable direction is to add more fine-grained recognition rules based on our refined PCFG, and another direction is to apply natural language processing technology to extract the password features. Last, we may use other methods to improve the model performance. This paper contributes to a better understanding of deep learning-based guessing models in that preprocessing indeed can effectively enhance the use of the neural network's learning ability, which is in turn intrinsically determined by the deep learning model's network structure. That's all we have to show you. Thank you for your listening.